In the first job I ever had in the electronics industry, we used this type of test meter. It's a Solartron 7045, 4.5 digits meter, quite accurate for its time. This was around 35 years ago, and it was deemed to be one of the best meters you could get at the time, unless you forked out for the extremely expensive 6 or even 7 digit meters. And say this is 4.5 digits, it's quite accurate, and it fulfilled the purpose that we needed it for. I found this one a few years ago on eBay, needed repairing, and just out of interest I bought it, repaired it, and don't really use it. It's just out of interest that I got it. The expensive meters that larger companies used back then were your 6.5 or 7.5 digit multimeters, usually rack mounted, extremely expensive. You know, we're talking sort of £20,000–30,000 for one. But these meters have now found their way onto the second-hand market, and so they're quite cheap, within the reach of enthusiasts or amateurs, and even new 6.5 digit meters are affordable. This leads us on to the point of this video, which is there are certain things you need to be aware of when you're using very high precision meters. And I've seen a lot of YouTube videos, friends using these high resolution meters, and not really understanding why the readings they're getting aren't always what they expect, or aren't stable. So they'll be trying to take a voltage measurement and it will be drifting and moving, and they assume it's just noise within the meter. But quite often it's not, and in the rest of this video I'll show some of the things you need to be aware of when you're using high precision multimeters. So before I start talking about measurement and measurement accuracy, I thought I would briefly mention thermocouples, because that is really what this video is about. A thermocouple is nothing more than two dissimilar metals joined together. So if you take a simple thermocouple like this that you've probably all seen, it's just two different types of metal welded together at the end. And the way a thermocouple works is anytime you bring two dissimilar metals together into physical contact or electrical contact, if you then apply heat to the junction, you will generate a voltage across that junction, and that is how we make use of them as temperature sensors. We just measure the voltage that they put out. It doesn't matter what the metals are, basically any metals will do. It's just that within thermocouples certain metal types are selected simply because they have good characteristics and give a good output. But any metal, or any two metals, will generate a thermocouple voltage if the junction is heated. And it doesn't matter if you're talking about the bulk of the metal object or if it's coated with a different metal. So if you get coated connectors, then the junction between the coating and the bulk of the connector is actually a thermocouple. And that is what this video is about. So with the increase in people getting 6.5 or 7.5 digit multimeters, the thermocouple effect becomes significant, and that's what I'm going to demonstrate in this video. This is a typical example of a 6.5 digit multimeter. It's an Agilent 344618. It's well within the budget of most amateurs and hobbyists, and it does a very good job. It's accurate, it's stable, and it has a lot of nice functions that are good to have. But one of the issues, as I said, is once you get above the sort of 4.5, 5.5 digits, you need to be aware of issues that you may encounter when you're trying to take accurate measurements. Now, although we're only looking at microvolts here, if you're not interested in microvolts, then you don't need 6.5 or 7.5 digit multimeters. So if you've gone to the time, trouble and expense of buying a 6.5 or 7.5 digit multimeter, The only way you're going to make use of the lower digits is to be careful in the way that you take measurements and be aware of what is contributing to those measurements. So to start with, I'll take a very simple measurement. I'm on DC volts, and if I connect one probe to one part of the ground plane on this board and the other probe to the other ground plane connection, so I've now got both probes connected to the ground plane, which you might think is a waste of time, but what I'm trying to demonstrate here is the effect of the contact point of the probes with the board. So if you see, we've got quite a stable reading on the meter. As you'd expect, we're just measuring across ground. But what you have to bear in mind is anytime we see a change in a voltage due to something other than the internal measurement system within the meter, that is superimposed on the meter measurements. In other words, you're adding to the overall uncertainty in the measurement that you're taking. So if I take a soldering iron, all I'm going to do is heat the board close to the probe. You'll see an initial jump, and that's because we've changed the loop characteristics in the measurement we're taking. So ignore the big step. If I take this off, you'll see we get a decaying value, and that is the board cooling down. It's not the leads heating up or anything like that. It's not the resistance of the board. It's actually caused by the thermocouple effect of the probes and their contact point with the board. If I now heat the other joint, or close to the joint, I'm not touching or bridging the joint, so we're now going positive. I'll take it off. You'll see it's cooling down, but it's cooling down from a positive voltage. And you're talking here sort of 30, 40 microvolts, which is quite significant when you're talking about a 6.5 or 7.5 digit meter. I'll go back to the other joint. Notice we've now swung negative. And that is the characteristics of thermocouples, is that if you heat one junction you'll go positive, and if you heat the other junction you'll swing negative. I can do the same thing by heating the probe itself. If I put the iron onto the probe, you'll see you get the same effect, much less pronounced. The probe obviously has more thermal mass than the board, but even so you can see that it is having a significant effect on the reading, and it is in fact in this case giving us an error of around 0.1 millivolts, which is obviously a huge error, but you can see as it cools down again it stabilizes. So moreover, if I heat the probe tip again, you see again we're starting to increase the voltage. If I now immediately move to heating the board, you'll see it gets even worse, because we've basically heated the entire joint, and that's generating a much higher output voltage. So this is just taking a simple measurement across a ground plane. I'm not measuring resistance, I'm measuring voltage. But you can see that we're getting readings, as I said, 6.5 digit meters, so we're getting an effect in the 4th digit. Now normally you wouldn't heat the board while you're taking a measurement, but bear in mind if you've just replaced the components and you want to take a measurement, then the board may be hot. You're holding the probe, so you're constantly warming them up, and I'll now show you what the effect can be of just simply warming up the probes with your hands, and it again can have a significant bearing on the reading that you're seeing. So I'll just change the probes. So what we're looking at now is just two banana type test leads, one connected to the positive terminal, one to the negative, and the other two ends are just shorted together. And although you wouldn't take measurements like this normally, as I said earlier, the point is that any errors that we introduce here will be superimposed on the actual reading you're trying to take, and obviously it will add to the uncertainty or the accuracy of the reading. So if you observe the reading, and I'll just hold one of these plugs in my hand, so I'm holding just one of them, and you'll see that the reading starts to drift. Now this meter's been on for a while now, so it's not caused by the meter itself drifting. So it's gone up by about a microvolt. So if I put that back down, you'll see that after a minute or so it will start to drift back down again. And that's as the junction temperature cools back down. Okay, so it's about a minute later, the reading has gone back down by a little over half a microvolt. If I now hold the other plug, so I'm holding effectively now the other side of the thermocouple joint. This is just in my hands, and it's quite cold in here, so my hands are not particularly warm. You can see now that the voltage is drifting the other way by a significant amount. You know, we're talking up to a microvolt or more, and that's just with a few degrees in changing temperature. So I'll put that back down and let it start to equalize again. But as I said, it might only be a microvolt or so, but if you're not interested in the microvolt or so, then you don't need 6.5 digits. If you are using 6.5, 7.5 or more digits, then this is very significant because it is swamping your lower 2 digits. Okay, so it's about a minute later, and you can see the voltage is getting back towards where we started. If you want to have a clearer look at what's going on, what we can do with this meter is put it into a trend chart mode, where it will effectively display the voltage over a period of time as a chart. So I'll zero it, and I'll allow it about 5 minutes now to equalise and settle down, and then I'll come back to it. So it's had about 5 minutes now to settle down. It's still drifting very slightly, but you can see most of what's on the display now is just noise, and that's largely because we got some fairly long leads straight across the bench. But if I now get hold of one of these two plugs, I'm going to get hold of effectively one side of the thermocouple junction. You'll see that as soon as I do that, there may be a small blip in the readings, and that's just caused by the me changing the loop characteristics. But what you can see now is that the voltage has gone off scale. So I'll auto scale this, and you can see that my holding this is having a significant effect. Auto scale again, and we've now changed by well over a microvolt from where we started. So the display is now showing between -2 microvolts and +1 microvolt, and it's still climbing. I'll now let go of the connector, and we can watch the effect as the temperature of the connector drops back down towards ambient. So you can see it stopped climbing, and it's starting to drop back towards where it started from. Now if you look at this, you can see that we went up by about 4 microvolts, which is a very significant error if you're trying to take 6.5 or 7.5 digit readings on a circuit. In my business, we quite often need to take very accurate voltage measurements down to a fraction of a microvolt. And so we do need to be fully aware of what effect the probes are having, and even take special precautions in terms of the way we set up the measurements to make sure that the readings we're taking aren't dominated by thermocouple effects in the system that we're trying to use. So you can see it's starting to drop back down towards where it was, and it will eventually settle back down to where it started. But what I'll do now is get hold of the other side of the thermocouple junction, the other test lead, and as that starts to warm up, you can see it's not instant, it's not due to capacitance or inductance. As it starts to warm up, you'll see the temperature rate will start to increase. So you can see it's starting to accelerate downwards at an ever increasing rate as the connector warms up, and now we've gone off scale negative, so I'll auto scale that again. It's continuing to drop, so I'll now put this back down, and then as the temperature of the probe starts to head back towards ambient, you'll see the voltage will also start to go back towards ambient, or at least the value it had when it was at ambient temperature. So again, as you can see, we dropped by about 4 microamps, so we've now changed the voltage that we're displaying. We went plus 4 microvolts, and now we've gone down by 4 microvolts. That's an 8 microvolt change in the reading that we're seeing simply by handling the probes. And this is just one end of the probe and one junction. Obviously the system effects can be much higher if you have multiple junctions, as we do. We've got junctions at this end, so if you take a probe from your probe rack and it's cold, room temperature, the instrument's quite warm, you plug it in, then you will see a sudden step change over sort of 5 or 10 minutes in the readings you're taking. And also, as instrumentation warms up, one of the reasons you get drift is because of the thermocouple effects on parts of the system that are not within the measurement loop. You'll get even worse effects if you start using things such as this, which obviously clip onto the end of your standard probe, because you then introduce yet another thermocouple junction where the two plug together. And if you're handling this, or if it's resting on something warm, so if it's resting on the board and the board's warm, or you move it around, then again you're going to get quite significant effects in the thermocouple effect, and it will be seen as inaccuracy in your readings. So there's various things you can do to avoid this. The first thing is obviously keep as few joints in the system as you can. If you don't care about the the few microvolts error that you're getting, then just switch your multimeter into a lower resolution mode, and you can then probably ignore it. But like I said, if you do need to use a 7.5 digit or even a 6.5 digit meter as we've got here, you can see that if you are trying to extract the best accuracy out of it, this is most definitely something that you need to be aware of, because as I said, we are looking at the bottom 2 or 3 digits at least of the measurement accuracy of the machine. You can see now we're pretty much back to where we'd started from. This same thing will happen. It doesn't matter which junction you warm up or cool down. If I hold one where it goes into the meter and I allow it to start warming up, you can see that already it's started to drift back down again. And that's already about half a microvolt that it's changed by, and you'll get the same thing if I hold the bottom one, it will drift up. Unfortunately, when you're testing equipment, you do tend to hold on to the probes and they do tend to warm up. That's one of the reasons why probes are long and have insulation. It's not just for electrical safety, it's to try to isolate the temperature drift at the tip of the probe. And by the same token, if you're using these, try to keep the overall temperature of the system you're trying to test as low or as stable as you can. You can then zero out the error and you'll reading should be far more accurate. So in other words, allow everything to settle down, plug your probes in, put your board that you intend to test, get it all powered up, get the temperature stabilized before you start taking readings. If you can, connect your probes to the test points, leave it for 10-15 minutes, allow everything to stabilize, zero out the error that you're getting, and then start taking your measurements. In other words, if you can, do this with the probe not quite in contact with the point you're trying to measure, let it all settle down, zero out the error, and then start taking your measurements. Just bear in mind that the longer you hold the probe for, the warmer it's going to get, and the bigger the error you'll see. If I hold on to this for long enough, I'll get probably a 5 microvolt error, and as I said, that is quite significant when you're talking about a 6.5 digit meter. So I hope you found that useful, or at least interesting. It is something that I do come across quite a lot when I'm trying to develop the equipment that my company creates. And it is something you most certainly need to take account of if you are using high precision equipment.